Hey everyone, my name's Max Leamy, and today I'll be presenting the Choose Your Own Adventure Lab. As an introduction, in this lab I chose to complete a lab that is purely an experiment, and I used Tracker to analyze the change in position of the pendulum of the corpus clock. I filmed the video used for the lab while I was in London for the break. After tracking the pendulum's position, I used many of the physics concepts from class to calculate the force the motor exerts to keep the pendulum constantly swinging and advancing the clock. For my results, I found the motor exerts a force with a magnitude of 0.0488 newtons. For the physics concepts in the experiment, the energy principle, Newton's second law, expression for the work done by a non-constant force, and the expressions to find translational kinetic energy, gravitational potential energy, and work done by a simple pendulum were used. The energy principle and various energy equations aid in calculating change in energy and net force for the pendulum during its swing. Newton's second law was used to aid in verifying the change in position and velocity observed during the experiment. I also tested whether the pendulum observed the energy principle, including multiple factors described later. For the experiment, I used Tracker to analyze a video of the change in displacement of the very tip of the pendulum needle of the corpus clock. I set the calibration distance as the diameter of the clock, which is 1.5 meters. The pendulum moves a mechanism called a grasshopper escapement to turn gears in the clock and advance the hands of the clock forwards. The initial position of the mass is 0.198, 0.001350 meters. The initial velocity of the mass is 0.86, 0.2120 meters. The initial velocity was found by observing the change in the x and y positions of the clock of the pendulum during the first frame of the video when the pendulum begins its upward swing. The system of the experiment is the pendulum, and the surroundings are the earth, the hands of the clock, and the motor. The pendulum was observed to swing in the same path over and over again, so it appears that total energy of the pendulum stays constant over time. The change in energy of the system of the pendulum should be equal to zero because the pendulum constantly swings in the same path if the motor is assisting it. From the experiment and design of the clock, I observed that the pendulum length is 2 meters and the weight of the pendulum is about 8 kilograms. I then created the energy principle statement for this experiment. Delta K plus delta U is equal to work done by air resistance plus work of the motor plus work done by the hands of the clock. The energy principle statement applies to the pendulum as it moves from the lowest point of its swing to the highest point of its swing, where it is momentarily at rest. To calculate delta U, I found the change in y coordinate of the pendulum during one half swing and used the formula delta U is equal to mg delta h to find that delta U is equal to 2.9 joules. To calculate delta K, I used the magnitude of the initial velocity vector I found earlier and observed that the velocity of the pendulum at the very top of the swing is equal to 0. I plugged these values into the equation delta K is equal to 1 half mvf squared minus vi squared and found that my delta K is equal to negative 2.9 joules. The magnitude of delta K is equal to the magnitude of delta U, so my energy principle statement can be simplified to work done by air resistance plus work done by the motor plus work done by the hands. The graphs of the x position of the pendulum head over multiple swings and the y position of the pendulum head over one full swing are present. The video became too blurry over time, so I could unfortunately only track the y coordinate of the pendulum over one swing. To calculate the work done by air resistance, the motor, and the hands, I first found the radius of the gears inside the clock. I assumed the work done by air resistance is equal to 0 to simplify the experiment. The work done by the grasshopper entrapment hands can be represented by a non-constant force of a constant A, which is equal to the ratio between the pendulum length and the gear radius, times mg sine theta plus force of motor. The change in position is equal to the change in radians of the gears from one pendulum half swing. The work done by the hands is shown on screen. To calculate force of the motor, I found the work done by the motor by multiplying force of motor by the change in position, the circumference of the gear multiplied by the radian change of one half swing. I then plugged all these values into the energy principle statement and found the force of the motor to be 0.0488 newtons. For the discussion, from the diagrams I observed that both the x and y position versus time graphs represent a pendulum swinging with zero energy change, as the pendulum returns to the same position it started in with a symmetric arc. As expected, the change in gravitational potential energy was found to be extremely close to the magnitude of the change in kinetic energy for the pendulum, so it obeys the energy principle. The force done by the motor is small and in the direction of the pendulum's motion. Some possible error of the experiment could be due to poor use of tracker, only using one swing interval for the change in y position, error calculating and defining change in energy and work done by the hands and the motor, and error from assuming work done by air resistance is equal to 0, as well as error when finding dimensions of the pendulum and the gear. Thank you so much.